faithfully reproducing the visual characteristics of reference images is challenging. In this work, we propose attention distillation, a unified approach to visual characteristics transfer. Visual characteristics transfer refers to the process of applying the distinctive visual style of a reference image, e.g. texture, style, and appearance, to a target image while preserving the target's original semantic structure as much as possible. The core challenge lies in striking an optimal balance between style migration and content retention. A classic approach to this challenge is style-content disentanglement. For instance, the seminal work by Gatiss et al. Leverages features from different layers of convolutional neural networks to separately represent image style and content, and achieves feature transfer by optimizing the style and content loss functions. Visual characteristics transfer demonstrates significant application potential across various domains, including image editing, artistic creation, and stylized rendering. However, existing methods suffer from notable limitations in generation quality and generalizability. Current approaches typically treat texture, style, and appearance as distinct tasks based on their specific characteristics. In contrast, our work aims to develop a unified framework for high-quality and universal visual characteristics transfer. Classic approaches have focused on designing visual loss functions to measure visual differences, subsequently achieving visual feature transfer through either image optimization or model training. These loss functions can be broadly categorized into two primary types. The former employs statistical distributions of images as visual features, emphasizing the pursuit of global distribution matching, while the latter prioritizes semantic correspondences in localized regions to achieve semantically coherent feature transfer. A representative example is the classical gram loss. However, this loss mechanism is limited to capturing second-order statistical differences, often leading to visual artifacts. Subsequently, Heitz et al. Introduced the sliced Wasserstein distance loss grounded in optimal transport theory. This loss function enables more accurate alignment of feature distributions, thereby enhancing synthesis quality. Zhou et al. Proposed the GCD loss, which strategically bridges traditional texture synthesis techniques with deep learning frameworks to enable more precise and controllable synthesis. However, these methods suffer from an inherent imbalance between global and local. Furthermore, these approaches predominantly rely on the VGG network for feature extraction, an architecture known for its limited capability in capturing nuanced style representations and semantic relationships. In recent years, diffusion models have garnered significant attention for their exceptional image generation capabilities. A prominent example is Stable Diffusion, a latent diffusion-based text-to-image model whose denoising network, UNet, integrates convolutional layers with self-attention and cross-attention mechanisms. Building on this architecture's attention mechanisms, researchers have developed a series of KV injection methods for visual feature transfer. These approaches achieve visual consistency without requiring model fine-tuning or iterative optimization. Master control injects key-value features into self-attention layers to enable consistent image synthesis and editing. The self-rectification algorithm proposed by Zhou et al. Combines structure-preserving inversion with KV injection to generate high-quality non-stationary textures. StyleID introduces a training-free style injection method capable of arbitrary style transfer. CIA focuses on zero-shot appearance transfer through cross-image attention mechanisms. At its core, KV injection operates by computing similarity scores based on the spatial information of the generated image through the attention mechanism, thereby dynamically aggregating visual information from the reference image. This process inherently establishes a global modeling framework rooted in localized semantic correspondences. However, current KV injection-based methods still exhibit limitations such as image quality degradation and insufficient stylization. We attribute these shortcomings to three primary factors. 1. Domain gaps between source and target images. 2. Inherent architectural constraints of diffusion models. And 3. Error accumulation during multi-step generation. To address these challenges, we propose a novel visual loss function built upon CVPR that achieves balance between global and local. Specifically, in the self-attention module of the diffusion model, we computed two branches. One is the attention output obtained through KV injection, which we regard as the ideal stylized result, and the other is the self-attention output of the currently generated image. The difference between these two is defined as the attention distillation loss. The goal is to distill visual styles from the attention mechanism of the diffusion model. To preserve the content, we designed a query-based content loss function. This loss operates on the query vectors of the self-attention module, ensuring that the generated image remains semantically aligned with the target image in terms of structure. With these two loss functions, we can perform visual feature transfer through the classic iterative image optimization approach. Additionally, we propose an attention distillation guided sampling strategy. Inspired by and improving upon the concept of classifier guidance, this strategy integrates the attention distillation loss with the model's denoising process. Specifically, during each denoising step, we compute the gradient of the attention distillation loss and use it to adjust the model's prediction direction. This guides the model to generate images that not only align with the text description but also exhibit the desired reference style. Our experiments cover the following 4 tasks. First is the classic texture synthesis task. Our method effectively handles textures at different resolutions. Compared to previous approaches, it generates more coherent and natural global structures, while also excelling in local details. Additionally, spatial control over texture structure can be further refined using masks or layouts. Compared to GCD, our method produces smoother edges, and compared to self-rectification, it remains more faithful to the example texture. Next is the style transfer task. These images demonstrate the transfer results across various artistic styles, including sketches, oil paintings, and modern flat or minimalist styles. Our method achieves impressive results in all cases. Here is a comparative analysis. Our approach preserves both stylistic appeal and realism, whereas competing methods often suffer from insufficient stylization or visual artifacts. Our method also handles appearance transfer effectively. Here, a structure image defines the shape and pose of an object, while an appearance image provides its material and color. Our approach accurately transfers appearance features, producing natural and photorealistic results. In contrast, competing methods exhibit issues like oversaturated colors or structural collapse. Finally, we demonstrate style-specific T2I generation. Leveraging attention distillation, we can provide a style reference image alongside a text prompt to generate results that align with the textual content while embodying the artistic style of the reference. As shown, the identity features of these celebrities are fully preserved and seamlessly integrated with the style. Comparative results with related methods highlight our approach's superior ability to capture and apply styles from reference images. Here, we present an ablation study on content weight adjustment. By tuning this parameter, we achieve varying levels of stylistic abstraction while ensuring smooth identity transitions in appearance. Our method can also be easily integrated with existing techniques. For example, combined with ControlNet, it enables structural control using depth or edge maps. Paired with multi-diffusion, it generates ultra-high resolution and high-quality texture images. In conclusion, in this work, we proposed a novel attention distillation loss that effectively extracts and transfers visual characteristics, including texture, style, and appearance, from reference images. Additionally, we introduced a corresponding attention distillation guided sampling strategy, seamlessly integrate loss into the diffusion model's generation process to extend its applicability. In essence, we present a unified approach capable of handling a diverse range of visual characteristics transfer tasks.